This short video presents an overview of 802.11be modeling in MATLAB. It is based on release 2023A of Wireless LAN Toolbox. Wireless LAN Toolbox supports physical layer and MAC and system level modeling of the IEEE 802.11 series of standards. At the physical layer, you find models for transmitter, propagation channel, and receiver. The typical measurements of interest are packet error rate and EVM. At the MAC and system level, it introduces MAC frames with detailed headers and scheduling concepts such as RTS-CTS and EDCA, along with the ability to look at throughput and latency due to channel contention in the presence of multiple stations. Wireless LAN Toolbox release 2023A supports draft 2.0 of the 802.11be standard, and we actively update the toolbox as the standard matures. It supports most features including 4096 QAM modulation and increased bandwidth of 320 MHz, both of which increase the maximum possible data rate that 802.11be offers. EHT, multi-user packet format generation and decoding, with multiple resource unit assignment and preamble puncturing, and phase rotation for the 320 MHz preamble. Generating 802.11be waveforms with Wireless LAN Toolbox is very similar to any other standard and happens in two steps. Step 1, specify the 802.11be configuration. Step 2, invoke the waveform generator. This slide shows a simple example code to do so. You select the channel bandwidth and then, for any user, the desired MCS. Here we select 12, which corresponds to 4096 QAM with a 3/4 coding rate. We generate a payload and invoke the Wireless LAN waveform generator to generate the waveform. Increased bandwidth and higher order modulation are but two aspects of the exciting new features in the 802.11be standard. Improvements in resource allocation such as multiple resource units and additional flexibility in channel puncturing are also of great interest. And they are shown in detail in the waveform generation example that ships with Wireless LAN Toolbox. Here's a look at this example in MATLAB. It shows many different possible configurations for waveform generation, as shown in the table of content. Let us look at two of these configurations. First, punctured packet generation with large MRUs. We set up a multi-user MIMO 320 MHz configuration for 2 users with puncturing field value 3. This puncturing value of 3 indicates that we are puncturing the third 40 MHz channel as shown here. As a result, the overall assignment shows users 1 and 2 assigned throughout the 320 MHz with one 40 MHz channel punctured. Then let's look at preamble puncturing for ORFDMA transmission. You can see that the requested configuration uses 2 allocation indexes, 64 and 26, to characterize 8 RUs. Those indexes are defined in the standard. 26 represents a punctured 242 tone RU, while 64 represents a single user 20 MHz channel. Therefore, that configuration with 5 64 indexes represents an assignment to 5 different users occupying 20 MHz each, with RUs 2, 6, and 7 punctured. When you generate the waveform, you can clearly see that those 3 RUs are punctured, including both preamble and data. Once you have generated an 802.11be waveform, you can build an end-to-end example using a propagation channel and receiver. Wireless LAN Toolbox includes different types of wireless LAN specific propagation channels, including the TGX channel. The TGX channel lets you configure many different types of impairments with fading, line of sight or non-line of sight conditions, depending on the transmit-receive distance, antenna configurations, and propagation conditions such as shadowing and path loss. It was updated to support 300 MHz bandwidth. You can also use ray tracing as provided in Communications Toolbox to compute the channel between the access point and the station. You can compute up to 10 reflections of walls, ground, and objects. In addition, Release 2023A introduces the ability to include diffraction effects. Once you have the waveform and simulated the impact of propagation, you can set out to determine the overall performance of the link at the output of a receiver. This is what the example shown here does. The receiver detects packets and processes legacy and then EHT-specific fields before demodulating, equalizing, and decoding EHT data. Let me point out that you have full source code, which means you can view, modify, or completely replace the receiver provided with the toolbox. Let us have a quick look at this example in MATLAB. The first step is similar to what we saw earlier, in that we set up the EHT configuration of interest, here at 20 MHz bandwidth with 4096 QAM modulation and 2x2 antennas. Next, we set up the propagation channel as TGax model B. The first two lines of a loop are a complete 802.11be transmitter and 2 lines of MATLAB, which is very powerful. After propagation and addition of noise, you can follow every step of the receiver through the code, all the way to the final decoding of data. Here you can see the code for channel estimation, demodulation, and equalization. At that point, we can compute the resulting packet error rate. If you run the simulation for a range of MCSs, you obtain waterfall curves as shown here. Of course, you may also want to perform simultaneous transmission to several stations. This is one of the major features in 802.11be, and this is what this example does. It computes the throughput achieved by sharing the available time-frequency resources among several stations using multi-user MIMO or OFDMA. Transmission to each station is optimized by computing the best precoding option based on channel information gathered from null data packets. Another crucial capability in 802.11be is trigger-based uplink transmission. This new example in Release 2023A uses trigger-based format to synchronize uplink transmission for several stations. On the access point side, the receiver uses successive interference cancellation to retrieve the packets coming from all users. The final capability I want to mention is EVM and spectral characteristic measurements. With higher bandwidth and increased modulation order come greater requirements on the RF portion of the modem. Being able to assess the impact of RF components on the resulting spectral purity and EVM is therefore more important than ever. In this example, we demonstrate how to set up a simulation with the multi-user 802.11be waveform, model RF impairments, verify compliance with the spectral emission mask and spectral flatness requirements, and measure the modulation accuracy, or EVM. You first select the number of packets and idle time between packets, then the exact configuration you want to test. For OFDMA, we pick a 3RU and 3-user configuration with different modulation encoding schemes per user. You then specify the oversampling factor to use to represent bands adjacent to the generated signal. We then generate the waveform. Before performing measurements, we specify RF impairments such as high power amplifier nonlinearities and thermal noise. On the receive side, we downsample and filter the waveform, and then feed it to the receiver we saw in our previous example. Let me run the example. The receiver recovers the cancellation for each user, as shown on this figure, and measures the EVM of the data for each one of them. Here we can see that the EVM is around -49 dB for all of them. You can also observe the spectral characteristics and spectral flatness of the waveform. To conclude this short video, we have seen that Wireless LAN Toolbox offers comprehensive support for 802.11be, with support for most features according to version 2.0 of the draft standard. Wireless LAN Toolbox is an open environment as it includes full MATLAB source code of transmitter, channel, and receiver, and you can interface your MATLAB session with instruments or SDR boards. The models are useful both for engineers looking for access to waveforms for further testing of their system, as well as engineers developing 802.11be algorithms who are interested in the detail of the standard. To learn more about Wireless LAN Toolbox, please visit our homepage at mathworks.com/WLAN or the wireless communications homepage shown on this slide.